new world. The Red Planet has a story, and it begins now.
Mars Saga presents another detailed exploration of the Red Planet, focusing on one of its most overlooked yet powerful systems, the Martian atmosphere. At first glance, this atmosphere appears thin, weak, and almost insignificant compared to Earth. However, closer observation reveals that even this fragile layer of gas plays a major role in shaping the planet's environment, surface, and long-term evolution. The atmosphere of Mars is composed primarily of carbon dioxide, making up more than 90% of its total volume. The remaining portion consists of nitrogen, argon, and trace amounts of other gases. Despite its composition, the total pressure of the Martian atmosphere is less than 1% of Earth's. This means that the air on Mars is extremely thin, offering very little resistance to external forces and very limited ability to retain heat. This thin atmosphere is one of the main reasons Mars appears cold and dry today. During the daytime, especially near the equator, sunlight can warm the surface to relatively moderate temperatures. However, because the atmosphere cannot trap heat effectively, this warmth quickly escapes into space as soon as the sun sets. As a result, temperatures drop sharply at night, creating extreme differences within a single day. These temperature changes directly affect the surface of Mars. Rocks expand slightly during the warmer periods and contract during the colder ones. Over long periods, this repeated cycle leads to the gradual breaking apart of solid rock into smaller fragments. This process contributes to the formation of fine dust that now covers much of the planet. Wind plays a central role in the Martian atmosphere. Even though the air is thin, it can still move dust and small particles across vast distances. Winds on Mars can travel at high speeds, especially during seasonal changes. As they move across the surface, they lift dust into the air and carry it across regions, slowly reshaping the landscape. One of the most powerful atmospheric events on Mars is the dust storms. These storms can begin as small disturbances caused by localized heating of the surface. As warm air rises and cooler air moves in, winds strengthen and begin to lift dust particles. Under the right conditions, these small storms grow larger, merging with others and eventually forming regional or even global dust storms. Global dust storms are among the most dramatic events on Mars. During these storms, a thick layer of dust spreads across the entire planet, blocking sunlight and significantly reducing visibility. The surface becomes hidden beneath a suspended cloud of fine particles. These storms can last for weeks or even months, during which the planet undergoes noticeable changes in temperature and surface appearance. The presence of dust in the atmosphere also affects how light behaves on Mars. Instead of a clear blue sky, the Martian sky appears hazy and reddish. This is due to the scattering of sunlight by fine dust particles. The color of the sky can change depending on the amount of dust in the air. During intense storms, the sky becomes darker and sunlight reaching the surface is greatly reduced. Seasonal cycles have a strong influence on the Martian atmosphere. Mars has an axial tilt similar to Earth, which means it experiences seasons. However, its orbit around the Sun is more elliptical, causing some seasons to be longer and more intense than others. These variations affect wind patterns, temperature distribution, and atmospheric pressure. At the polar regions, seasonal changes lead to the formation and disappearance of carbon dioxide ice. During the winter, temperatures drop low enough for carbon dioxide gas in the atmosphere to freeze directly onto the surface, forming thick layers of ice. This process reduces the overall atmospheric pressure across the planet. When spring arrives, the ice sublimates back into gas, increasing the pressure again. This cycle repeats every Martian year and plays a key role in atmospheric dynamics. The interaction between the atmosphere and the surface is continuous. Dust is lifted into the air by winds and later settles back down onto the ground when conditions calm down. This constant exchange shapes dunes, covers older geological features, and creates new patterns on the surface. Over time, this process smooths certain areas while exposing others. Another important aspect of the Martian atmosphere is its interaction with solar radiation. Because Mars lacks a strong global magnetic field, high-energy particles from the Sun can reach the upper atmosphere and gradually strip away gases. This process has been occurring for billions of years and is believed to be a major reason why Mars lost much of its original atmosphere. Evidence suggests that Mars once had a much thicker atmosphere, capable of supporting liquid water on the surface. Valleys, river channels, and lake beds indicate that water once flowed freely across the planet. A thicker atmosphere would have provided higher pressure and warmer temperatures, allowing water to remain stable. Over time, as the atmosphere was lost, these conditions disappeared, and Mars became the cold and dry world seen today. Despite its current state, the Martian atmosphere still shows signs of activity. Instruments have detected trace gases that appear and disappear over time. One of the most discussed examples is methane. While the source of methane on Mars is not fully understood, its presence suggests that active processes may still be occurring beneath the surface. The thin atmosphere also affects the stability of water on Mars today. Liquid water cannot remain on the surface for long because it either freezes or evaporates quickly. However, under certain conditions, especially when mixed with salts, small amounts of liquid water may briefly exist. These flows are temporary and leave marks that fade over time, indicating ongoing interactions between the surface and the atmosphere. Dust devils are another visible sign of atmospheric activity. These small, rotating columns of air move across the surface, lifting dust and creating narrow tracks. Although they are much smaller than large dust storms, they are common and contribute to the continuous movement of surface material. The study of the Martian atmosphere relies on data collected by orbiters and rovers. Orbiters observe large-scale patterns, such as global dust storms and seasonal changes, while rovers measure local conditions, including temperature, pressure, and wind speed. Together, these observations provide a detailed understanding of how the atmosphere behaves. Understanding the Martian atmosphere is also important for future exploration. Any human mission to Mars will need to deal with challenges such as low pressure, radiation exposure, and extreme temperature changes. At the same time, the atmosphere offers potential resources. Carbon dioxide can be used to produce oxygen and fuel, which could support long-term missions. Scientists continue to study how the atmosphere of Mars evolved over time. By comparing current data with geological evidence, they aim to reconstruct the planet's past environment. This research helps explain why Mars followed a different path from Earth and how planetary systems change under different conditions. Mars remains a world of quiet but continuous activity. Its atmosphere, though thin, drives processes that shape the planet in subtle but significant ways. Winds move dust across continents, seasonal cycles change pressure and temperature, and solar radiation continues to influence the upper layers. What appears to be a still and silent planet is in reality a system of ongoing change. The Martian atmosphere may be weak, but it is not inactive. It connects the surface, the climate, and the history of the planet into a single evolving system. Through continued observation and exploration, the atmosphere of Mars reveals more about the planet's past and provides clues about its future. Each new discovery adds depth to our understanding, showing that even the thinnest layer can hold the key to an entire world.